nanoparticles. For your syllabus, I have kept only silver nanoparticle synthesis. Okay, this process involves reduction of metal from its metal ion solution using a reductant. Okay, reductant may be trisodium citrate, or it may be sodium borohydride, or it may be formaldehyde, any reducing agent. Reducing agent means which gives out electrons. Okay, reducing agent gives electrons, and the other that metal ions, they accept the electrons and deposit as metal or settle as metal. Okay, the nucleation process follows when colloidal metal is formed from metal ion. Metal ion accepts. Okay, right. So metal ions, I cannot write here, so I have to download that app. Okay, anyway, I'll just give in brief. Okay, metal ions, they accept electrons, depositing as metal. Okay, reduction technique. Reduction method, reduction means accept the metal ions accept electrons and become metal. Okay, which has got zero state. Oxidation state is zero. Okay, so we call it as nucleation process. The right colloidal metal is formed. Okay, the metallic nucleus expands as more metallic atoms diffuse through the solution and bind to it, and it grows. The metal grows. Okay, metal atoms grow. Okay, and they form a nanoparticle. We can control this. When the concentration of metallic ions drops significantly, what it is no longer feasible for metallic ions to join together to form a new nucleus. Okay, what happens in this process? What happens? So metal ions are forming metals at this time. Okay, metal ion concentration is also decreasing. When it drops significantly, it will not create a new nuclei, and the growth also stops. Nucleation halts at this junction, and no fresh nanostructures are produced. The residual ions in the solution are absorbed by growing nanostructures. Okay, so usually reducing agents, reductants used here are trisodium citrate. Trisodium citrate is also used as capping agent. Okay, sodium borohydride is a reducing agent, and formaldehyde is also a reducing agent. Okay. In order to control the particle size, we usually use capping agents. Okay, capping agents like polyvinyl alcohol or polyethylene glycols are added just as capping agents. We don't want that nuclei to grow rapidly to become microparticles. We want to control them in nano size only. For that, we use capping agents so that the nanoparticles will not agglomerate. They will not join together. Okay. So this is about the chemical reduction method. Okay. In this chemical reduction method, we'll study the synthesis of silver nanoparticles. Characterization, anyway, it's the second unit. Okay. I'm just discussing only the synthesis. Okay. Synthesis of silver nanoparticles. So there are two methods. Okay. Silver has been used throughout the history. You may be knowing in India also, not Greeks and Romans. Indians also used to store water in silver vessels. Okay, silver utensils were used earlier. 1800, silver was used to treat ulcers. 1880s, silver nitrate eye drops were given to newborns, new babies, to like antibiotic drops. It's a silver is a antibiotic. Okay, in 1920s, silver was used to manage wounds. Okay, currently there are many products they use silver and silver nanoparticles. Okay, so presently we use washing machines, okay, which contain silver nanoparticles. Hair straighteners, athletic clothing, socks, they all use diabetic socks. They use silver nanoparticles. Okay, so they have got antibacterial properties. Okay. How we synthesize nanoparticles? There are basically two methods. Okay, metallic nanoparticles can be synthesized through many methods. Two most popular methods of synthesizing nanoparticles via chemical reduction. As I mentioned, what is chemical reduction? Metal ions are used and reducing agent is used. Okay, reducing agent reduces the metal ions to metal nanoparticles. Okay, there are two methods. One is Turkevich method in 1951, he gave this method of preparing silver nanoparticles. Okay, he gave a method for silver particles. Okay, now we are preparing silver nanoparticles by this Turkevich method. Silver is reduced by trisodium citrate. Trisodium citrate is a reducing agent. This is a reducing agent. Okay, for example, we use this to give electrons. Okay, anyway, I'll discuss in a little bit in detail. Okay, and another method is there, Brust method. Okay, in 1994 it was developed by Brust. Okay, this is produced using sodium borohydride. Okay, we will discuss both. Okay, Turkevich and Brust method. Okay, Turkish method of nanoparticle synthesis. What they do usually use the hot silver nitrate solution. Okay, they have used 60 ml of 0.001 molar. That is 1 millimolar. 1 millimolar is nothing but 0.001 molar. Okay, very dilute solution of silver nitrate. We boil it. Okay, this reaction takes place at higher temperatures. So while stirring, we keep it on a magnetic stirrer. You have seen magnetic stirrer, and we heat it to around 60 to 80 degrees Celsius. Okay, 80 degrees Celsius minimum. Okay, above that, okay, we keep always. Okay, we boil this solution, and while stirring, we usually use magnetic stirrer. Okay, then when it is boiling, we add 6 ml of 10 millimolar, means 10 times more concentration than silver nitrate. What we use? Trisodium citrate. Okay, concentration of trisodium citrate is 10 times more than silver nitrate. Why we use? Because we want to reduce all silver ions. That is the reason we use excess trisodium citrate, which can also act as capping agent here. So this we take it in the burette. Okay, trisodium citrate we take it in the burette. Okay, and drop wise we add 1 drop per second to a beaker or any conical flask which contains silver nitrate solution of this concentration. Right, dilute silver nitrate solution. 1 drop per second I am adding. Okay, or sometimes you can add 1 drop per 2 seconds. As slow as possible, you have to add trisodium citrate with stirring. Okay, then what happens? You wait for the solution to change. You close it. Okay, wait for solution to change to light golden yellow. You get this color solution. It's not silver color, it is yellow color solution. Carefully remove the beaker from hot plate and let the solution cool. Okay. See, at the macro scale, silver is always looks like white shiny metal. Okay, but solutions of silver nanoparticles. Okay, you can see the colors. Okay, yellow. Okay, right, slightly orange. Okay, you can see different colors here. This is because of plasma resonance. I'll be discussing when I discuss the properties. Okay, you don't worry about this plasma resonance right now. Okay, why the color looks like that? It's because of vibrate oscillating electrons present on the silver nanoparticles. They give this color. Okay, these oscillation affect the light interaction with nanoparticles. That is the reason they are of different colors. Okay, if you take absorption spectra, okay, its visible range 400 to 700 nanometer. Okay, you can see the color. Okay, at 400 nanometer it is violet. Okay, what will be the size? Okay, 10 nanometer. 20 nanometer also has got this similar size. Okay, similar color. Right, different colors you get. Okay, yellow to right, all the colors you see. Okay, colors we see basically an integration of absorption spectra. Nanoparticles size can be monitored more accurately by taking absorption spectra. Okay, if you observe absorption spectra here, if you observe this is the spectra, greenish color, then the size may be around 30 nanometers. Okay, if it is yellow, what will be the size? 60 nanometers. Okay. If it is blue, dark blue, okay, if you observe 410 nanometer absorption, means which is in blue range, so it is 40 nanometer. Okay, you can see different colors. Okay, well, this is the reaction. You, instead of auric chloride, you take silver nitrate here. Okay, the same silver nanoparticles and cover it with trisodium citrate ions. Okay, they reduce silver ions. Instead of gold, you mention silver ions and cap the resulting nanoparticles. They cap it so that agglomeration will not take place. Very simple. Okay, so this is about synthesis by which method? Turkevich method. Okay, there is another method, brush method. Same thing you have to follow. Okay, instead of 60 ml of point, the same thing, you should not boil it. In brush method, you cool it to 0 to 5 degrees Celsius. In brush method, what do you do? Yes, anyone? Anyone is listening? Please respond.
Yes, sir, listening.
Yes, instead of boiling, we are cooling it. Okay, in brush method, and instead of trisodium citrate, what we are using? Sodium borohydride. What is the difference? We are not boiling here, we are cooling it in brush method. Okay, as rest of the things are same. You have to stir it, you have to use same concentration of silver nitrate and same volume. Okay, it is not boiling. Once it is cooled, add 6 ml of 10 millimolar what? Sodium borohydride, drop wise, one drop per second. Okay, that method is called brush method. Okay, so these two are the chemical reduction methods of preparing silver nanoparticles. Okay, in the examination, I may ask you, explain any one method of preparing silver nanoparticles. You can explain Turkevich method or brush method. Okay, in Turkevich method, we use trisodium citrate. In that, 1 millimolar silver nitrate is boiled. 60 ml of 1 millimolar silver nitrate is boiled. Then we add dropwise trisodium citrate. Okay, 10 millimolar of 6 cc. Okay, 6 cc of 10 millimolar trisodium citrate we add. Okay, in brush method, silver nitrate is first cooled. Okay, the same 1 millimolar silver nitrate solution of 60 ml volume is cooled first. Then we add sodium borohydride 10 millimolar, 6 ml of 10 millimolar sodium borohydride dropwise. Is that clear to you?
Yes, sir.
Okay. So these two are the methods for your syllabus. Okay. You right. So we'll ask, explain any one method of synthesizing silver nanoparticles. 5 to 6 marks. Okay. So explain it. Okay, or both the methods. Turkevich method, we use trisodium citrate as reducing agent. Okay. And in both the cases, you need to write this chemical reduction. This is common. Okay, chemical reduction method, this part is common. The next is in Turkevich method, we use trisodium citrate. In brush method, sodium borohydride. Okay, well, so now we have prepared the nanoparticles. Okay, next is characterization. Okay, so we discussed different methods of synthesizing nanoparticles. What are they? Top-down approach and bottom approaches. Okay, both the methods I've discussed already. Okay, so that is first unit. Now we will go to the second unit. That is characterization of nanostructures or nanoparticles. Okay, so how to characterize nanoparticles? What are the ways? Can we see nanoparticles?
No, sir.
No, we cannot see nanoparticles with our bare eyes. Even with optical microscopes, we cannot see. Why we cannot see?
Size is small.
The size
Size.
of very good. The size of the nanoparticle is so small. It's smaller than the wavelength of visible light. What is the wavelength of visible light? 400 nanometers. Right? At the max, highest optical microscope you can see is around 250 right micrometer. Okay, so 250 nanometers. Okay, right, less than that we cannot see because it is limited by the wavelength of light. See, this is a particle. Okay, imagine this is a particle. Wavelength is so big. Wavelength of light is bigger than the particle, so it may not hit. It may not hit, so we cannot see it. Is that clear to you? There is no interaction of light with the nanoparticles. If the size is invisible light, I am talking about the visible light. Of course, if you use ultraviolet lights, okay, there is chance of hitting, but we cannot see it. Okay, is that clear to you?
Yes, sir.
So here, what we do is we use electron microscopes. Okay, so you use electron gun. What is the size of electron? 10 raised to minus 18 meters, right? So it can you can image it with electrons, right? So that is the reason we use electron microscopes. There are advantages of electron microscope or light microscopes. Okay, what is the difference between electron microscope and light microscope? Okay, the source is beam of electrons in electron microscope, whereas in light microscopes, illuminating source is light. Okay, visible light. Here, it is very large and complicated system. Electron microscope, if you ask, we may ask, what is the difference between electron microscope and light microscope? It is very large and complicated. Microscope, usually light microscope, is very compact and handy. But the problem is you cannot see nanoparticles. Only fixed specimens are studied. Here you can study the living and fixed specimens. Everything you can study here. The object is ultra thin. It should be less than 0.1 micrometer in case of electron microscope. Whereas in light microscope, object is little thicker, around 5 micrometer or thicker. Only dehydrated specimens are used because when you are using electrons, okay, electrons, if you heat water, water will absorb all electrons, so you cannot see the specimens, okay, nanoparticles. Here the specimen need not be dehydrated. Dehydrated means removing of water. Here you need to remove the water, electron microscope, whereas in light microscopes you don't have to dehydrate it. And this is very important. Electron microscope requires what? Vacuum. If I take electron gun and fire it, the air will absorb the electrons. Okay, so I need to create what? Vacuum. There should not be any interaction. Okay, there should not be any collision with the matter. Okay, the air. Okay, the atoms present in the environment. Okay, oxygen, nitrogen, all the gases are there. Okay, they will absorb electrons. Right, they are much bigger than the electrons, so we have to remove it. So we require highest possible vacuum, whereas vacuum is not required for light microscope. It requires very high voltages. Which one? Electron microscope requires high voltages because you need to create electrons with the electron gun. Okay, so I'll be discussing in detail anyway how we generate electrons. And there is no need for high voltage or electricity. Okay, even in presence of light, you can observe the specimen with light microscope. This I think you used if you have taken what the biology in PUC level. Okay, you might have seen the light microscope. Tungsten filament is used to produce electrons. How you produce electrons? You require a cathode. Okay, where you where you apply very high voltage, so electrons come out of tungsten. Okay, so tungsten filament is used, or lanthanum hexaboride can be used as uh, electron gun. Okay, to produce electrons. Filament is not required because you are not producing any electrons in this light microscope. It has a cooling system to take out the heat generated by high voltage electric current. You require very high voltage, so again cooling system is required in case of electron microscopes. There is no cooling system required for light microscope. There is a risk of radiation leakage in case of electron microscope. There is no radiation risk in case of light microscope. It employs electromagnets. See, you used light microscopes. They use lenses, optical lenses, which are made up of glass or quartz. Right. Electron microscope, if you use glass, if you fire electrons, the glass will absorb all the electrons. So what is required? You require some coils like this. Okay. For example, like this. Imagine 4 poles. Okay. What I'll do? I'm firing electrons like this. Okay. And these two are oppositely charged. This is negative charge and this is positive charge. So electromagnetic field is generated there. Okay, electric and magnetic field is generated. So electron, okay, with AC, okay, we connect it to AC. So once it comes here, okay, it is attracted towards what? Electron is repelled by the negative charge, but it is attracted towards the positive charge. But positive charge becomes negative charge. It is alternating current. Okay, so it goes like this, spiraling down and goes down, goes straight. So we are collimating the electrons. That you are getting the parallel, instead of parallel light, you are getting parallel beam of electrons. You got it? You require electromagnetic lenses, not the optical lenses. Optical lenses will absorb electrons. So what we require? We require electron lenses. Okay, electromagnetic lenses. So which focus the beam of electrons towards the specimen. Okay. So image is formed due to scattering of electrons. In case of electron microscope, image is formed due to absorption of light. In case of light microscope, image is only on a fluorescent screen. Here in electron microscope, image can be seen directly with your bare eyes. Specimen is coated with heavy metal in order to reflect electrons. So that specimen should be conducting. Okay, you have to make it conducting in case of electron microscope. Otherwise, the electrons will not be scattered or this one. Okay, if it is if it is not conducting. So for that, you coat some metal on the surface. Okay, you spray some metals on the coat on the surface of the specimen. Okay, nanoparticles also you put some what do you call metals. Okay, so that you can visualize it with electron microscope. And here specimen is stained by colored dyes in case of light microscope. In case of electron microscope, the image is black and white, no color image. Whereas in light microscope, you get colored image. Resolving power is 0.5 to 5 angstroms. Okay, so it can be up to 0.25 angstroms theoretically. Very high resolving power with electron microscope. Resolving power of light microscope is 250 nanometers or 2.25 micrometer. Okay, so below that it cannot see. It cannot resolve. Resolving power, you know, I think in schools, you might have studied. There are two objects which are very close, and the distance between the two objects is 250 nanometers. So normal optical microscope will not resolve these two. It can see only one. Is that clear to you?
Yes, sir.
So, but if you use electron microscope, you can see these two are separate. I think you might have seen stars. Okay, two stars, if they are very close by, we think that there is only one star. Okay, one star is here, another star is behind this, but the angle is less than say 0.1 degree. So we see only one star. So if we have very good telescope which can resolve that also 0.1 degree, you can see that two different stars there. Is that clear to you? So we have electron microscope which has got higher resolving power. Okay. Magnification up to 3 lakh. You can magnify the image up to 3 lakh times. Magnification up to 4,000 times in case of light microscope. See the difference. This is because of electrons. Okay, and their sizes are so small you can easily image the nanoparticles. Okay, nanoparticles 10 raised to minus 9. Electrons size is 10 raised to minus 18. Hope it is clear to you. So they are so small. Okay, when you fire them, okay, wherever the gap is there, okay, they can easily pass through and they form an image, black and white image. Okay, it is called transmission electron microscope. There is another microscope that is scanning electron microscope. That what happens when the electrons fall, they're hitting the specimen. When they hit the specimen, the electrons are scattered. Okay, secondary electrons we say. Okay, because of that we get scanning. We can scan them. Okay, scattered electrons we collect and we create the image. That is called scanning electron microscope. And you remember, transmission electron microscope is of higher resolution than scanning electron microscope. Okay, so you know the difference between electron microscope and light microscope. Which microscope we use it in the characterization of nanoparticles?
Electron microscope.
Electron microscope. It's clear to you. Okay, and this question definitely will be asked. Okay, what is the difference between electron microscope and light microscope? Okay, so now we go to transmission electron microscope. This TEM is commonly known as TEM, transmission electron microscope. It was first demonstrated by Max Knoll and Ernst Ruska, okay, in 1931. Okay, it was first developed in 1931, demonstrated in 1931. With this group developing the first TEM with the resolution greater than that of light. Okay, less than 400 nanometers. Okay, our light microscope around 250 nanometers. Okay, less than that. Earlier there were no instrument to separate them, resolve them. Okay, resolving power was maximum is 250 nanometer. Anything less than that we cannot see, we cannot resolve them. Okay, now in 1933 they first developed this. In 1931 they developed, and commercial one was developed in 1939. Okay, and in 1986, okay, Ruska was awarded with Nobel Prize. Of course, Ernst was there. Ernst, right? The Nobel Prize usually is given to the person who is alive. Okay, Ernst Ruska was there. Okay, so he got the Nobel Prize for that. Max Knoll was not there, so he didn't get the Nobel Prize for that. But anyway, this was done by both Max Knoll and Ernst Ruska. So what is this TEM? Transmission electron microscope. It's also known as conventional transmission electron microscope. Is a microscopic technique which a beam of electrons, like we use an electron gun, is transmitted through a specimen to form an image. The specimen is most often an ultra thin section of like 100 nanometer thick, okay, and it is suspended on a grid, okay. An image is formed from the interaction of the electrons with the sample, okay, specimen, okay, as the beam is transmitted through the specimen. The image is then magnified and focused onto an imaging device such as fluorescent screen you can use, or a layer of photographic plate or film sensor such as CCDs, okay, can be used. TEM are capable of imaging at a significant higher resolution than light microscope, as I mentioned, even scanning electron microscope also. I'll be discussing that in the next class. Owing to a smaller de Broglie wavelength of electrons. Wavelength associated with the electrons is very less. De Broglie theory you might have studied. Have you heard about this de Broglie?
Yes, sir. In physics.
In physics, yes, yes. This enables the instrument to capture fine details because whatever the wavelength associated with the electron is so small, much smaller than the size of nanoparticles. So you can easily resolve them because whatever the wavelength we are talking about in lights, it's up to 400 nanometers. Okay, we can see up to 250 nanometers. We can use the light to resolve the two images, two specimens, right? This is commercial instrumentation, okay. Right, it usually contains an electron gun and condenser aperture, okay, specimen port, objective aperture, okay, diffraction lenses, okay, then projector lenses, binoculars, okay, imaging recording system, okay. When you draw in the examination, you draw this diagram. This is much simpler diagram which I have made, okay. Right, here what we use an electron gun. Okay, same diagram you draw in the exam. Electron gun we use. This is electron gun. Okay, electrons are fired. Okay, you require a condenser lens. See, it's not normal optical lens. It is actually we have what we have is electromagnetic rods. Okay, like this. Okay, 4 rods or 8 rods. Okay, which are connected to alternating current. Two poles are opposite poles are same charge. Okay, what happens? So this is the one. Okay, imagine this pole and this pole is negatively charged. This pole and this pole is positive charge. Electron comes here like this, so it is attracted towards the positive charge, but it is connected to a AC source. It becomes negative charge. Anode becomes cathode and cathode becomes anode. 50 hertz. Okay, sinusoidal AC. So electron comes near, but it becomes negative charge. It pulls back. It pushes back the electron. So electron rotates like this and goes straight without hitting the lens. So it is collimated. And we have one more set of condenser lenses. Then we have scanning coils, and we have objective lenses. Okay, so the same electromagnetic lenses where we keep the sample here, and then it is images formed on the photographic plate or fluorescent plate. This is the structure. Everything, whatever I had drawn here, it is inside a vacuum chamber. Everything is inside the vacuum chamber. So I'll be discussing a little bit about what is emission source. Emission source or electron gun. Okay. So this structure is like this. This is mounting connectors. Okay. This is a support, and we use a small filament, tungsten filament, or you can use a needle or lanthanum boride single crystal source. Okay. Here we use lanthanum boride crystal or tungsten filament, which emits the electrons. Okay, so when you apply high voltage, typically about 100 to 300 kilovolt. We apply this much of voltage. What happens? Electrons are emitted by the source. What is the source? Here we use tungsten filament or needle, or we can use single crystal lanthanum hexaboride, LaB6. lanthanum hexaboride. The gun is connected to high voltage source. This is high voltage source, typically 100 to 300 kilovolt. And given sufficient current, the gun will begin to emit electrons either by thermionic or field electron emission into the vacuum. Okay, the electron source is typically mounted on Van Heldt cylinder. Okay, this is typically mounted on a Van Heldt cylinder to provide preliminary focus of emitted electrons into a beam. Okay, the upper lens, this is of TEM, then further focus the electrons to desired size and location. Okay, so this is about the electron gun. Okay, where how we generate the electrons. Electrons are generated using tungsten filament or lanthanum hexaboride single crystal source. In the examination, you can draw this diagram. If the question is asked on emission source or electron gun, you draw the diagram, then mention what crystal we use, lanthanum hexaboride or tungsten filament, and what is the typical voltage we apply, 100 to 300 volt, kilovolt. Okay, so this much, even if you write, is sufficient. Okay, it's electrons are emitted by thermionic emission or field emission, field electron emission. Okay, so and this, what if, it is typically mounted on Van Heldt cylinder. Okay, which provides preliminary focus of emitted electrons. It contains electromagnetic lenses. That's it. Okay. Then you require what? Vacuum system. Okay, to increase the mean free path of electrons, electron gas interactions. Mean free path means, for example, two electrons are here, okay, and one gas is here, electrons are here, they collide. There should not be any collision. Okay, the electron should not collide. So electrons should not collide means you require what? Vacuum. So what is the highest possible vacuum? Is 10 raised to minus 4 pascals. 10 raised to minus 4 pascals, or if you write it in torr, 10 raised to minus 11 torr, or 10 raised to minus 11 millibars. Okay, is that clear to you? So evacuated to low pressure. So that mean free path means how much the electrons travels, the length, the length of the electron. Okay, it means the path length of the electron without any collision. We call it as mean free path. Okay, an electron travels 10 centimeter without any collision. That means what is the mean free path of the electron? It is 10 centimeter. If electron travels 100 centimeters without any collision, then its mean free path is 100 centimeter. If an electron, okay, if there is a gas, okay, what is the mean free path? Say maybe micrometers or millimeters. Okay, electron comes out, it hits the air, the gas molecule. So that's the reason we create a vacuum. So when we create a vacuum, there are no gases present, so electron can travel longer distance. Okay, the need for this is twofold. First, the allowance for the voltage difference between the cathode and the ground without generating an arc. See, so you need to create a negative charge so that it pushes the electron, and you need to apply positive voltage on the other side so that electron travel in this direction. Electron gun, okay, that is negatively charged, and the other one is anode is positively charged. So there is a potential difference, a huge potential difference. What is the voltage? 100 to 300 kilovolt. So that much voltage in air, it creates what? Sparks. Okay, arcs. Okay, arc is created. If there is no air, no gases, then that arc is not produced. Okay, so you don't get any fire hazards if it's a vacuum, total vacuum. Okay, secondly, it reduces the collision frequency of electrons with gas atoms to negligible levels. This effect is characterized by what? Mean free path. So that's the reason we go for vacuum system. Why we go for vacuum system? One, we are applying very high voltage. There should not be any spark or any arc should not be produced. Okay, in vacuum, arc is not produced. Okay, and and also to increase the mean free path. These are the two reasons why we go for vacuum system. Electromagnetic lenses. Okay, electromagnetic lenses are designed to act in a manner emulating the optical lens by focusing parallel electrons at some constant focal distance. Okay, so electron lenses may operate electrostatically or magnetically. Okay, electromagnetic lenses, these are the majority of electron lenses used for TEM. Usually they are magnetic coils. As I told, coils generate a convex lens. Okay, they use coils to generate a convex lens, so that for example, negative charge is applied. So what happens? Electron is also having negative charge. It is repelled. Okay, and the other side you have applied very high positive voltage. So electron is attracted this direction, and here you are applying negative charge, so that it converges. If you use positive charge, it diverges. Okay, it is attracted, but you are pulling the electrons by applying very high positive voltage on the other side. Electron is generated and very high positive voltage is applied on the other side below the specimen or near the specimen, so that electron should move in that direction. Is that clear to you? Electron lenses are manufactured from iron, cobalt, any magnetic alloys, okay, such as permalloy. Okay, these are selected for their magnetic properties, such as magnetic saturation, hysteresis, and permeability. So basically, we are using electromagnetic lenses, and you see here very small pinhole. We call it as aperture, so that any electron is not in this axis should be excluded. If it comes here, okay, if it comes here, it will hit and it is scattered. Okay, it will not be transmitted through this aperture. Aperture is a small pinhole. Okay, so it allows only the electrons which are moving in this direction only. Okay, optic axis we say. So apertures are annular, the metallic plates through which electrons that are further than the fixed distance from the optic axis may be excluded. So if the electron is going in this direction, it will be excluded. Only the electrons which are moving in this particular straight direction, okay, in the axis, they are allowed to pass through. Okay, and that is the main reason of aperture. There is no other reason. And it also decreases the beam intensity. Okay, and they filter or remove the electrons that are scattered to high angles. Only the electrons with perpendicular, which are moving in 90 degrees, okay, they are taken here. Specimen stage, where you keep the TEM sample support a metal grid. Okay, it is usually made up of gold or copper or platinum or molybdenum. Okay, specimen stages are used. The usual thickness, the diameter is around 3 millimeters. Okay, approximately 2.5 to 3 millimeters, where you keep the sample. Okay, specimen stage we call. Okay, on this we keep the sample, and the thickness of the mesh, this mesh is around 100 micrometer. Okay, and this specimen stage designs include air locks. So we can take out this specimen and keep it without losing the vacuum. Okay, if you open everything, air will enter. Okay, only these specimen stages can be taken out with minimum loss of vacuum, because creating a vacuum takes days. Okay, you require 2 days to reach that vacuum, 10⁻⁴ Pascal. To reach that vacuum, you need to keep the turbomolecular pumps continuously evacuating the system for 2 to 3 days. Even small moisture will increase the pressure inside. Okay, it should be total vacuum. How you do that? We use very high turbomolecular pumps, and for that, okay, if you want to, because specimen stage you are removing and keeping the sample most of the time. That's the reason it should be excluded. Okay, from the earlier, that high vacuum, this one. So only this part is taken out, and you can again it is connected to separately to a evacuating system, the pumps. Okay, suction pumps. Okay. So finally, display system. Okay, imaging system in TEM consists of phosphor screens. Okay, usually we use zinc sulfide. Okay, nanoparticles. Okay, or microparticles. Okay, when the electrons hit, they fluoresce. Okay, the phosphor. Okay, images you can see the image. Optionally, an image recording system such as film-based or Doppler screen coupled with coupled CCDs. Typically, these devices can be removed or inserted into the beam path by operator as required. The display system can also be removed or inserted where you don't require, right, very high vacuum, right, creation can be done within a day or within a short period of time. So I'll stop here. Okay, if you have any questions on TEM, the characterization means the nanoparticles you cannot see, so you have to rely on electron microscopes, and also you can go for probe microscopes. See, this is my hand. Okay, either I can see it or I can feel it. How the blind sees. Okay, slowly I can move this cantilever or my other hand, so I can create an image in my brain. Okay, this is called atomic force microscope. Okay, or they are known as probe microscopes. Okay, either you can see the nanoparticles or you can feel it. You cannot see the nanoparticles, you can image the nanoparticles either by electrons or by using probes. Probes just move the cantilever, and how the blind see. Okay, blinds cannot see, blind person cannot see, but he can feel, he can create an image. Okay, he just uses his hand with other senses. Okay, and generate an image. Okay, the same is used in electron microscope. Sorry, atomic force microscope, AFM. Okay, I'll be discussing that AFM in the next class. I'll stop here. Any questions, please ask.
So can you send the first unit PPT, sir?
Yeah, right now I'm just uploading it in Google Classroom.
Okay, sir. Thank you.
Okay, fine. Any other questions? Any other questions?
No, sir, no question.
Please just give your attendance in this one, in the chat box. Just type your name, your USN, your USN is better. Your name and your USN. So any questions you can ask me meanwhile. Eight members are not there. 29 members. Do they know that we have online classes? Do they know? They have, right? They are part of our this one WhatsApp group. Okay, all of you have recorded your attendance. Okay, we'll exit the meet.
Okay, sir.